Hello, my name is Tristan Mathis, and today I will present my project idea, which is performing LiDAR-based assessments of tree canopy structure and distribution in the State College region using LiDAR data. Using high-resolution LiDAR data, I aim to map vegetation, understand how tree cover varies across the landscape, and visualize patterns relative to urban development. The goal is to provide clear spatial insights into where trees are located and how green space is distributed. My motivation and significance is I believe urban tree canopy is critical for healthy, sustainable communities. Trees filter pollutants, moderate temperatures, and enhance neighborhood aesthetics, supporting residents' physical and mental well-being as people participate in outdoor activities. Accurate information about tree canopy is essential for city planners. We use it to identify areas lacking vegetation and prioritize new planting. LiDAR data provides us high-resolution 3D point data that allows us to precisely map trees, their canopy coverage, supporting better decision-making than traditional aerial imagery or satellite data. My project objectives for this study will include identifying trees and vegetation using LiDAR, mapping canopy coverage across different land use types, comparing patterns between urban and forested areas, and visualizing these patterns relative to roads and other infrastructure. I aim to generate maps and 3D scenes to clearly show where vegetation is often concentrated. As I mentioned prior, this study focuses on State College and surrounding areas within Centre County, covering approximately 8.25 square miles. To accomplish this, I will use the 2019 North Central Pennsylvania LiDAR dataset, which provides high-resolution classified point clouds for ground, vegetation, and buildings, along with digital elevation models. I will use the tile index data to efficiently select the relevant tiles covering the study area across the north and south regions. In addition to this, with the LiDAR, I will incorporate the PatMap roads layer and Centre County open data land use to examine tree canopy relative to urban infrastructure and land use. This combination of LiDAR and vector data allows for 3D mapping of trees, canopy coverage, and their spatial relationship with streets and other built features. These datasets support analysis relevant to urban planning, green space management, and environmental monitoring within Centre County. My methodology for this study will first be pre-processing the LiDAR data to remove noise and verify the classification of points into ground, vegetation, and buildings. I will then generate surface models, specifically a digital terrain model from ground points and a digital surface model. Next, I will filter the LiDAR point cloud to display only vegetation, creating maps that show the spatial distribution of trees across urban and forested areas. I will also then overlay road and land use data from the PatMap roads layer and then the Centre County open data land use layer to examine how vegetation relates to streets, neighborhoods, and other built features. Finally, I will interpret the results by identifying areas of dense versus sparse vegetation and summarizing how canopy presence varies across urban and forested zones. These steps will produce detailed maps and rasters that support analysis of tree distribution and canopy coverage throughout the study area. I expected our preliminary results from the analysis. I expect to identify areas with the highest and lowest tree coverage, measure average tree heights, and visualize canopy distribution. These results will help provide insight into urban green space, as well as areas where planting initiatives could be prioritized. Utilizing the LiDAR data, I expect to produce a vegetation distribution map showing the locations of trees and other vegetation across State, College, and the surrounding areas. By analyzing these classified points, I anticipate being able to identify areas with dense versus sparse tree coverage and examine how canopy presence varies across the different land uses. I expect that high vegetation areas will correspond to parks, forested parcels, and mature residential neighborhoods, while lower vegetation will likely be observed in urban cores, along roadsides, and in commercial zones. Integrating road and land use data should allow me to explore how development patterns influence tree distribution. Finally, I plan to calculate summary statistics to estimate vegetation density or relative canopy coverage across urban, suburban, and forested areas, providing a clearer picture of expected spatial patterns of the urban tree canopy in the study area. Lastly, the applications and significance of this study. From the results of this project, it could support several practical applications for urban planning and green space management. They can help planners identify neighborhoods or parcels with limited tree cover. helping prioritize planning initiatives and making informed decisions about managing urban vegetation to improve aesthetics and recreation. In terms of environmental monitoring and ecosystem assessment, the analysis provides a baseline of vegetation distribution that can be used to track changes over time. It helps support evaluation of canopy density, tree maturity, and overall green space quality, and can be combined with land use and road data to understand patterns of vegetation connectivity or fragmentation. Overall, the study demonstrates the practical value of remote sensing and GIS for supporting sustainable urban forestry, environmental monitoring, data-driven planning decisions.